Okay, so there were 4 slides that we didn't have a chance to get to in the lecture today. And so I'm going to go over each of those 4 slides. The first 3 have to do with force as a vector. So this is emphasizing F equals ma in 2 dimensions, where not everything just lies along the line. And then the last example, it looks like it's 2D, but it kind of simplifies to 1D, so we can get around this. But yeah, let's look at some 2D problems. So the first thing is to draw a free body diagram for a book of mass m just sitting on a ramp. So we're told in the problem statement that we want to focus on the book, right? So we're going to draw just the forces acting from outside the book on the book, right? There's more than one thing going on. There's more than one object that appears here, right? There's this force probe, there's a ramp, there's the wall. But focusing on the book, looks like we can draw some forces acting on it. So the first one that's easy that you can always draw right away is the weight, so mg, that's pointing vertically downwards. So then you could take a step back and say, well, okay, let's pretend that was the only force acting on the book. Then the book would be accelerating downward 9.8 meters per second squared. But it doesn't do that in this problem, right? There's a ramp in the way that's preventing the book from crashing into the ramp. So the way the ramp does that, prevents it from crashing through, is providing a normal force that is perpendicular to the ramp's surface. So the ramp has a surface that's like this, and then also into and out of the screen. So that's 2 dimensions. And then the third dimension is perpendicular to both of these. So one of these 2, and it's pointing away from the surface. So there's a normal force that looks like this. And so I want to show actually, so we can show that this angle right here, the angle that the normal force is from the vertical direction, is the same as this angle right here, the angle that the ramp is inclined. And the best way to see that is to take your hand. So like right now, my thumb is pointing in the horizontal direction, my finger's in the vertical direction. And then I'm just going to rotate, so I'm going to keep these perpendicular to each other. I'm going to rotate my thumb so that it's lining up the ramp. So if I rotate it in amount theta, so in other words, I'm taking this, and I'm rotating this in amount theta, then I'm going to rotate this in amount theta as well. So the direction that's perpendicular right here, the normal force direction, is an angle theta relative to the vertical. Right? So that's a handy trick to keep in mind for a lot of these ramp style problems. Okay, so these forces, because they're not in opposite directions, they can't cancel each other out. So the next question is, okay, is the book actually accelerating in a direction that's the sum of these 2 forces? No, probably not, right? It looks like from the setup of this diagram, not only is the book not floating away from the ramp and it doesn't crash into the ramp, there's no indication that it could slide down the ramp because the force probe has a cord that's attached to the mass, so it's preventing it from sliding down. So it looks like maybe it stretches out and the force probe has some reading on it. So this cord is preventing the book from sliding down. There's a tension in that cord right there. And these 3 forces can sum up to give you 0 net force on the book. And it looks like those are the only 3 forces acting on it, on the book. There's no friction. So in most problems, you'd probably be told that it's a frictionless surface. Yeah. Okay, so let's move on to this part. What's the tension in the spring, as read on the force probe? So I'm going to copy down this free body diagram. There's the tension, there's the normal force that was at some angle theta here relative to the vertical. I'm doing a different color just to emphasize that I want to keep just the forces blue here. And then there's the weight. Well, you'll see why I elongated it in just a second. So there's the weight mg. Now for problems where you have a mass on a ramp generally you don't want to choose a coordinate system like what you're used to. So normally we're used to gravity being the minus y direction, and then the horizontal being the x direction. But for problems where you have a mass on a ramp, it's nicer to have a coordinate system where one direction is along the ramp, parallel to the ramp, and one is perpendicular to the ramp. It tends to make the algebra a little bit easier. So remember what I was talking about before with this and then rotated? That was also the coordinate system that you're rotating a little bit, right? So the coordinate system, it's not the horizontal and vertical like gravity and perpendicular, but along the ramp and perpendicular to the ramp. So, and I tend to choose the plus x direction to be down the ramp because that's where most of the action is most of the time. Most of the time, something's like sliding downward. I like to keep that positive rather than negative. Okay, so if we choose that to be our coordinate system, it looks like two of the vectors are kind of nice in that they just lie along one of those axes, right? The normal force is just in the plus y direction. The tension is just in the minus x direction. The gravitational force is a little messier though, because it has non-zero x and y components now. So I'm going to try and separate out the x component and the y component here. Okay, so the way you want to think about that is if you have a vector that you know there's x and y, non-zero x and non-zero y components, you want to think of the overall vector as being the magnitude of a right triangle, like the hypotenuse of a right triangle. And the other two legs are the piece of the vector that's along the y direction and the piece that's along the x direction. It's a right triangle. The magnitude of this vector is mg. And so now we have to figure out which of these two angles is theta. Right? Theta is some parameter of the problem. And I want you to focus on, there's this line and there's this line. And if you have two lines that intersect like this, the opposite angles have the same value. Right? So we already convinced ourselves that this was theta right here. So that means that this angle is the one that's theta right there. So those two are the same. And then these two are the same as well. But we don't need those angles for this problem. Okay, so with that angle and with mg, we can write this side as mg cosine theta. No, sorry, sine theta. And this side is mg cosine theta. We'll see why that's useful when we apply Newton's second law. So generally the strategy is as soon as you're done drawing the free body diagram, you want to apply Newton's second law. So Newton's second law says that the sum of the forces on the book equal to the mass of the book times the acceleration of the book. And in this problem, we're pretty confident the book's not moving, right? It's not allowed to slide down the ramp. There's no reason for it to go up the ramp. The force probe's just kind of keeping it there, and then it's not flying off the ramp or crashing into it. So it looks like this is 0. This is a vector equation. The sum of the forces is equal to the 0 vector. So we can separate this out into x and y pieces. Okay, so that if you have a force problem in more than one dimension, you want to separate out the x's and y directions here. Now the problem that we want to solve is what's the tension in the string. And so that's going to focus on the x direction. So I'm going to focus on the x direction with the equations right here. In the x direction, you want to take the x component of each vector and add them all together. And then that will give 0. So there's the gravitational force, x component, plus the normal force, x component, plus the tension, x component, equals 0. And notice how now it's not a vector equation anymore. Now it's just an equation of numbers. So each of these components can be a positive number, a negative number, or 0. And when we add them all together, we get just the 0 number, not the 0 vector. So the gravitational force, which is this one right here, the mg, the x component looks like this piece, and is it positive or negative? Looks like so this vector, the total hypotenuse of this right triangle, it's a sum of a vector that's pointing down like this, into the ramp, and then along the ramp like this in the positive x direction. This means that the gravitational force has positive x component. So in other words, this is going to be mg, which is defined to be positive, sine theta. So that's positive, and there's a definite plus sign there. The normal force has no x component, right? It's totally in the y direction. So the normal force is n y hat plus 0 x hat. There's nothing there. And then the tension has x component minus t. So t is the magnitude of the tension force, but it's pointing in the negative x direction. So there has to be because t is defined to be positive, we have to manually insert that negative sign, because it depended on us introducing this coordinate system. If we introduced a coordinate system where the x direction was in the other direction, up the ramp, then these two signs would flip. Right? Instead of a positive and a negative number equaling 0, you would have a negative plus a positive number equals 0. But it makes sense that you can't have a positive number and a positive number equals 0, right? Or a negative and a negative equals 0. So that's a good double check, right? You're adding a positive and a negative number to give 0. And this tells you that the tension is equal to mg sine theta. That's the tension in the rope. So I'll fill in the steps here for when I post the lecture notes, but you should be able to convince yourself that what the y direction is going to tell you is that the normal force is equal to mg cosine theta, which you can kind of see from the diagram, right? These two have to be equal to each other in magnitude. But it's nice seeing how this works out with the free body diagram and then setting it up in terms of Newton's second law. Right now it seems like overkill, but for more complicated problems, you really want to just get in this habit and automatically do this, because for more complicated problems, you can't just see the answer, quickly like this. It's a lot. It's not quite as obvious. Okay. So here's a separate example regarding forces in more than one dimension. We have another box that looks like an envelope or something. So step one of all these problems is just to draw a free body diagram. It looks like we have some pulling force, and I'm not gonna, they already told us to use FP, so I'm not gonna label it something else. Might as well use what they already set up. So there's some pull, F pull, or F applied. A lot of times you would see in books. There's always mg. Looks like there's definitely gonna be a normal force, right? Because it's resting on a surface here. So you could maybe this person's pulling so hard that it lifts off the ground, but we don't want to enforce that from the beginning, right? There very well could be a normal force right there. Also, they really hint that there's a normal force right here. So the numbers are such that normal force will be there. And frictionless, so no friction there. Okay, so step one, identify the object as a box. Step two, draw the free body diagram. Step three is always apply Newton's second law. So sum of all the forces is equal to mass times acceleration. I guess I used a capital M here. And right now we don't know the acceleration. It says, find the acceleration of the box. So we can't just set this equal to 0. However, it says that the box is being pulled by an applied force, and there's no mention of it lifting off the ground. So, and I guess they even told us that there's a normal force there. So, if it lifted off the ground, there would be no normal force there. So the acceleration, we don't know its value, but we do know that it is equal to, we'll call this. So also notice how I didn't need a coordinate system until I'm applying Newton's second law. So the fact that I have vectors here and I want to deal with I have to deal with the separate components means that I have to introduce a coordinate system there. I didn't need one to draw a picture. But I'm going to call this the x direction, this the y direction, and the acceleration is totally in the x direction, or I hat direction. And the reason this is useful is that when we separately look at the x direction and the y direction, so the x direction is going to say the sum of the x components. So the ith force, the x component, this is equal to mass times the x component of the acceleration. And the sum of the forces, the y components, is going to be equal to m times ay, but this is equal to 0 because the box isn't lifting off the ground. Right. So if I look at the y direction and on the y components of all the forces, looks like all three have a non-zero y component. We have n is in the plus y, and all of it is in the plus y. And then FP, not all of it is pointing in the y direction, right? We have some angle theta. And it looks like the y piece right there is going to be FP times sine theta. Okay, so this is plus FP sine theta. Right, but still positive, right? The part of FP lying along the x direction points in the plus y rather than the minus y. And then minus mg is equal to 0. So the normal force, which is one of the things we're asked to solve for, is equal to mg minus fp sine theta. And we have all of the numbers right here, right? We have m, mass g is 9.8 meters per second squared, fp is this, and theta is 30 degrees. So we have enough to solve for the number right here. So some number of newtons. Right, as long as everything is at SI units, you'll get your number in newtons. Then the x direction, what does the x direction tell us? Well, if I look at my free body diagram, there's only the gravity doesn't have a x component. You know, the x component is 0. Same thing with the normal force. The only thing that has an x component is Fp. So Fp cosine theta is equal to m times ax. And so we're asked, what's the acceleration of the box? Well, it only has an x component, not a y component. And the magnitude of it is Fp cosine theta over m. And that will give you some number as well in meters per second squared. As long as Fp is in newtons, which that's what they gave us, right? And m is in kilograms, then the acceleration will be meters per second squared. So as long as, you know, if you have an equation and everything is in SI units on the right-hand side, then you're left with SI units for this quantity as well. So I'll plug in numbers when I post the lecture notes, but that's how you go about this. Same setup, right? Free body diagram, Newton's second law, separate the x and y directions, and they'll give you a different equation for each dimension. Okay, one more problem, and that's the acceleration of this system. So there's no friction. Remember, we had someone holding this mass here in place, and the tension here was m1g. And then we let go of that mass, and we were able to prove that the tension in the core decreased as a result of that. So if you weren't at lecture or you want to review that, now is probably a good time. Find the acceleration of the system. Okay, so we have two different free body diagrams. So just to remind you, there's m2g, lowercase m, m2g, there's a normal force on the table, and there's the tension. That's for m2. And then m1 has its own free body diagram. That's m1g, and tension is going up. So the pulley redirects the tension force, so it can pull on m2 to the right and pull on m1 upwards. But it's the same tension as long as the cord is massless. Now for each of these separate objects, Newton's second law applies. So you have sum of all the forces on m2 is equal to m2 times its acceleration of object 2. And then separately, you have sum of all the forces on m1 is equal to m1 times its acceleration. But these things are moving together, right? So as m2 goes this way, m1 goes down the same amount. So not only are their velocities are coupled, they're fixed as long as the rope is taut, T-A-U-T. So the velocity, the speeds are going to increase at the same rate, and they're going to have the same acceleration. So we're just going to call this the positive direction. This is positive direction, positive acceleration, positive direction, and this is a positive. Okay, so for M2, so focusing on this for a second, we have the sum of all the forces. So the normal and the gravitational force have to cancel each other out. So if we wanted to solve for the normal force, that's easy. It's just m2g. But we don't care about that because we're trying to find the acceleration of the system, which for m2 is going to the right. And it looks like the tension is equal to m2 times the acceleration of the system. Right? That acceleration is going to be to the right is the same thing as m1 going down. So if we look at m1 now, let's now look at this one. M1, so you might want to pause the video here and try and think about, if you're not familiar with the previous slide, you know, is M1G or is tension bigger? Which one's bigger and why? Pause it. So the answer is that M1G is bigger than the tension, right? Because this thing, you're releasing it from rest and M1 starts to accelerate downward, right? This thing goes from rest to going down. Right? There's no reason for it to go upwards. There's no reason for the tension to be stronger than that. Right? M2 would have to be pulling on it, but there's no reason that M2 would start pulling to the left. Right? So the reason I'm saying all this is that in my head, I know M1G is bigger than T. So when I write the following down, M1G minus T, so I'm trying to explain why I wrote it in this order rather than T minus M1G. When I'm writing this down, I know I'm writing down a positive number, right? M1G minus T is positive, and it's M1 times that positive acceleration that's going downwards for M1. So in this system of equations, we have two equations for two unknowns. Our two unknowns are the tension and the acceleration. So we can use our two equations to solve for the two unknowns. So a trick that I'm just scooting this over right here. So a common trick that we're going to use a lot actually is to solve by elimination. So solve by substitution, solve by elimination. There's equation 1 and equation 2. What if we added equation 1 and equation 2? Right, so in other words, take the left-hand side, add them together, take the right-hand side, add them together. And so you get a new equation that's also true. So this is equation 1 plus equation 2 at this point. So if I add these equations together, and the reason we're adding them together is that the tensions will cancel out if we add them together. Notice how we didn't have to scale either equation 1 or equation 2 up or down by any factor, because there's a t and there's a minus t. So we get this. And it looks like solving for the acceleration, we get acceleration as m1 divided by m1 plus m2 times g. So when you get an answer like this, you want to do a couple checks. So one checks. One, dimensional analysis. Dimensional analysis. If I look at a mass divided by a mass, so kilograms divided by kilograms, that's unitless, right? So the thing in parentheses has no units, has no dimensions. So it looks like we have the dimensions of acceleration, or g, as units, SI units, meters per second squared. And that matches acceleration. So that looks good. Now this doesn't guarantee our answer's right, but it would let us know if our answer was wrong if the dimensions didn't work out. Another thing we want to look at is limiting cases. So in other words, you want to check that your answer makes sense. There's a couple things you could think about in terms of M1 versus M2, right? If one is a lot heavier than the other one, does our answer make sense? So one of these is M1 much bigger than M2. So if that's the case, M2 is just like a speck of dust or something, and M1 is this heavy thing. If that's the case, it doesn't really take much of anything to accelerate the speck of dust, right? Imagine that the rope is tied to basically nothing. M1 is just going to fall down at G, 9.8 meters per second squared. So in other words, we would expect, so I'm not even looking at the answer right now. I'm just saying we would expect that in the limit M1 much bigger than M2, the acceleration of the system should be G, right? Because M1 is basically just falling on its own. There's nothing holding it back at all. And if you look at this formula, you plug in, you take the limit, and you've taken calculus, so you know how to take the limit as m goes to infinity. If that's the case, this is basically just M1, right? M1 plus M2. If M1 is really big, then that's the same thing as M1. So you have M1 divided by M1, and you get acceleration is equal to G. Okay, so that checks out. And then the other check you could do is, what if M1 is much less than M2? So in that case, you have like a speck of dust that's connected via a light massless cord to something that's on the table there. And so gravity is the thing that's responsible for the acceleration of the system, and it's not going to do much to a speck of dust. So it's going to the acceleration is going to be very small in that limit. And if you look at this, you have M1 plus M2 is basically just M2. You have M1 divided by M2 is a very small fraction, something much closer to 0 than to 1. So acceleration would be very small in that case. Looks like that checks out as well. Okay, we'll be doing more practice, obviously.